Just joined us, thank you very much for being with us during this Andela online technical workshop session. And I hope that you're going to find value from this. So Oded Coster, our speaker today, says that he first learned programming on the BBC Micro in the early 80s. More recently working on the Ethereum blockchain. Prior to joining Intelligent Hack, where he is currently the CTO, Oded helped organizations like Tesco, ASOS, Figley's, AKQA, and he was also a principal developer at Stack Overflow. So Oded, it's a pleasure to have you here with us. I hope you're going to also enjoy it as much as the participants here hopefully will. And yeah, over to you.
Thank you. Thank you for that lovely introduction, Mercy. I wanted to talk a bit about simple programming and why that should be where you really start and where you should try focusing yourself on. So this is Gall's law. I'll give you a minute to read that. And he was a thinker, and a doctor. But this is something that he found in research. You can't start building a complex system intending it to be complex. It is bound to fail. So start simple. So why is that? Well, simple is it's easy to understand. It is easy to modify. When you have a nice big group of people and new people joining your teams, it's a lot easier to get them started, get them to understand, get them to learn. Simple is a lot more accessible to people on very different levels. If you don't go simple, you end up with areas in your system that only specific people can work on. That is not good. You'd much rather have the ability of of as many different people at different levels being able to work on your systems. A lot of the time, what you see is not particularly surprising. What you see is what you get in a simple system. There are no hidden mines or areas where you go and something completely, you write code that you expect to do one thing and something completely different happens. Simple, when I'm saying simple, I'm talking about code, I'm talking about system design, I'm talking about the whole ecosystem, how you deploy your code, how the servers are set up, how they talk to each other. All of that, when I say simple, I'm talking about all the different parts. And when you go simple, a lot of the time you also go fast. So the more complicated you make a system, you tend to make it slower. So when I'm talking about what happens when you're working on a clever or a complex system, they're a lot harder to understand, modify. Again, as we said, difficult for people to understand, new people or existing people, not a large number of people can work on them. You have all kinds of areas where things are magical, things just happen and no one or very small number of people know exactly how these things happen. And other people just, I don't know how it works. I'll just follow the incantations to make it work. And as I said before, these kind of designs can also be a lot slower. So one of the things as software developers that we need to look at complexity is to understand the difference between accidental and inherent complexity. Inherent basically means that some issues and some problems that we need to solve are hard. They're just difficult in their nature, and that's inherently so. They are inherently complex. What we need to guard against is what is called the accidental complexity. It's all the other things that are required to make our systems. how we organize our code, how we structure it, our architectures, where we decide to make things more flexible versus more rigid. Where do we need that flexibility? How we decide to deploy things, how we decide to run them, how we decide to monitor them. Examples of things that might be accidental complexity. You have 6 files that you're working on, but you're putting them in 5 different folders. You know, consider, why do you do that? You know, maybe they can all be in one folder instead of just broken out. You know, it makes that a little more difficult to find things. Deeply nested namespaces in certain languages. You know, then, you know, again, difficult to find things, difficult to locate them, difficult to know where they live. You might have multiple projects or files or DLLs that you only ever deploy together. I'm talking here specifically about languages like C# and .NET that compile to DLLs, and those produce specific, each project produces a specific DLL, but if they all are deployed together, you know, you kind of need to think, why am I breaking them up into separate files to begin with? And apart from that, there are abstractions that don't really add anything to the code except for another layer. So where do we find complexity? So, and this is specifically the complexity, complex code versus just the simplest, easiest, most straightforward way of doing things, which is what I am advocating for in this presentation. So in decoupling, design patterns, solid principles, premature abstraction, useless codes, and over-reliance on libraries. There are other things. This is not exhaustive by any means. So I'm going to go through these one at a time. Decoupling code is good when you need the flexibility. Okay? Specifically when you need that flexibility, not before, not anticipating things. So because decoupling is not free. Every place where you decouple, you know, where you're introducing decoupling, it adds the complexity of your code. It makes it more difficult to make large-scale refactorings, in particular when you're using DI frameworks, because then you don't know what is used where, why it's being used. And a lot of the time, if you have a highly decoupled architecture, you get locked into that architecture and structure of code and those interactions. It's very difficult to see the whole and try to clean that up or work around it. So decouple when you need to, when you need that flexibility, but not before. So there is a trade-off here, and there are a lot of trade-offs in everything I say here. But in this case, a trade-off between the simplicity of that specific layer or class or module and the simplicity of the whole application, you know, or the whole system. You know, if we're talking about something like MVC, you know, if you put everything in the controller, then yeah, the architecture is very simple. Everything is in the controllers. But when you look at the controller, you have a mess. You don't know what's going on. If you do this on all your controllers, it's then difficult to say, actually, we have certain things that are common. You know, we need to do database calls a certain way, and maybe we need to change how we do the database calls. But now you have to hunt across all of these many different places instead of have it all abstracted into one place where you could just make the change in one go. Design patterns. Most design patterns actually add complexity. They tend to introduce new structures. Many of them have complex interactions. They can very easily lead to over-abstraction. And the main thing about design patterns is really that they should be something that is discovered. It's not something that you should just build in. It's not, you know, you either discover them while you refactor, or when you actually look at the patterns, what you're doing in code, and you look at those patterns yourself. So the main point here is not to say, I know I will use this pattern here, or I will use that pattern here. As you design the system, before you do that. The main benefit of design patterns, the way I see it, is one of communication. Is to be able, oh, okay, I see what you're doing here. You're using the repository pattern, or you're using that pattern. But you shouldn't start your system and say, I will be using these patterns. They need to emerge from the code base. With design patterns, one of the problems is that if someone is not actually familiar with them and familiar exactly with what you're doing, they can look very strange. One of the more complex design patterns is called the visitor pattern. It has a lot of moving parts, a lot of different classes interacting, and it could look really, really strange to someone who's never seen it before. Additionally, overusing design patterns can be slow. Eric Gamma, one of the group of four, who were the writers of the original seminal design patterns book, actually recounted a project where they had to remove certain design patterns, which made the code simpler, but because they were overused, caused the UI to be very slow. And that was a problem they had to fix. And the fix was to remove some of the patterns that they were using. And another thing that the group of four said is to favor composition over inheritance. So this is something as a rule of thumb that I find tends to get forgotten, that you don't have to just use inheritance all the time. Composition is not just a possibility, it's actually highly encouraged as the first approach. It tends to be simpler, it tends to be easier to understand, and there are many other reasons to go with it that I won't go into right now. So that was design patterns. Solid. I will go into each of these solid principles in turn. If you're not familiar, SOLID is the acronym coming from these four principles as SOLID. I don't know if people are familiar with them, so I'll just give you a minute to read all of these. Okay. I wanted to talk a bit about the problems that come with SOLID. No context to these principles. Following these solid principles may very well work for the kind of software that Uncle Bob was and is developing. But, in game development and web development and so on are a very different environments to the ones that he came from. Actually, Uncle Bob's background, he started at a telecommunications device of a industrial automation company. He was there for 12 years. Those were his first 12 years of software engineering. Most of that was in the 80s, so well over 40 years ago. We live in a very different programming and world than then. And the constraints that he had and the constraints that we have are very different. I think you tell a game developer that they should be following SOLID, they will laugh you out of a room. Because the constraints that they have and the things that they need, SOLID just will not work for them. It will actively work against what they need to achieve. If you need to paint a frame after responding to input within 16 milliseconds, if you want to reach 60 frames per minute, then introducing all these layers and this complexity makes it very, very difficult to make a performant game. So you won't see any game developer use SOLID unless they're very new to game development. These are not principles, not really. I mean, most of these are techniques or rule of thumb. If you look at principles and laws in other professions, they are much more global and are a lot more are difficult to dispute. We'll see a little later that they are actually self-contradictory to an extent. And the main thing is that they add or they assume certain complexities already exist. So the first principle, and I'm using principle as because that's just the name of it, is that a module should only have one reason to change, sorry. This adds complexity by encouraging decoupling. It means more classes, more interactions, versus the most simple way of doing things. Another problem here is that it's not very well defined as a principle. What's a module? What size is it? Is it a class? Is it a method? Is it an assembly? Is it a whole file? Who decides what the reason is to change? Is it a bug fix? Is that a reason to change? A change in requirements? A restructuring of the code? I think to me, all these are valid reasons to change any class. So one reason to change is very amorphous. The open-close principle. So this one adds complexity by encouraging deep inheritance hierarchies. It makes it very difficult to know where relevant code exists. And frankly, I've never seen it used anywhere. Again, it's a badly defined principle, but do note the previous principle. Our previous principle said that a module should only have one reason to change. This principle tells us that software entities should not be changed. So which is it? Should they be changed, or should they have one reason to change, or should they not be changed? So there is the contradiction, and I think the main contradiction I see in Solid. LSP, Liskov substitution principle, also paraphrased as code to abstractions, not implementations. This tends to be overused. You end up having interfaces that only have one implementation, a lot of decoupled code that doesn't really need to be decoupled. And most of the time, that's what I see. You don't really want to decouple stuff just to say it's decoupled. As I said about decoupling, use it when you need to, not just because you can. It's difficult to anticipate the future. I don't really know anyone who manages to do that to any extent. I will give an example from my not so distant past at a company where they wrote a whole data layer to be in interfaces with one implementation for one database system, because as they were building the system, which was to be sold to customers, they expected the different customers would need to be using different database systems. And that was a big assumption to make. And as far as I know, even today, after many years, that has never actually come to fruition. So they've put in a lot of effort in ensuring that their system can swap the database system that it uses to actually never do that. So again, don't make assumptions about what is in the future. Work with what you see and the requirements that you have in front of you. The next principle, and this one, in terms of complexity, the only thing I can say is that it just assumes that there is an inheritance hierarchy, that you need to implement interfaces and different interfaces. And in general, if you do have to, this is good advice, separate things out to be as coherent as possible in your interfaces. That will also keep your classes more coherent. In that respect, if you have to use an inheritance hierarchy, listen to this. And the dependency inversion principle. again, which is very similar to what we saw earlier with the Liskov substitution, only it comes into it from actually building dependencies. It's also known as the don't call us, we'll call you principle. Also, basically, most people understand it is a class shouldn't instantiate its own dependencies, it should be receiving them. How it should be receiving that is beyond this talk. But let's talk again, complexity here. Now the caller needs to supply the dependencies. You might have multiple callers and they, each of those might have different requirements and may end up having to supply a different dependency. So that adds a bit to the complexity. A lot of the time, they all need to supply the exact same dependency. So now we've pushed up the complexity of how to build the object or what it depends on to a caller. Sometimes this can lead to incomprehensible configuration, especially when DI containers are overused. And this assumes that all coupling is bad, that we just need, but the thing here is software needs to be able to call methods, to call each other. Things need to be coupled. If everything is completely decoupled, nothing can happen. So coupling is actually part of making software run and execute. So again, in the not so distant past, I've seen classes that take 20 or more dependencies. That was due to the DI system and container system on that specific platform, making it so appealing and easy to use that programmers just go, oh, well, yeah, I'll just add another dependency. I'll just add another list to the construction of this class. And because everything will happen automatically for me, I don't have to really worry about it. Which, to an extent is true, but again, it leads to complex code. It's difficult to know what is being called, why it's being called. It's difficult to know to follow the code, to know what is happening where, what is going to happen where, and why. You don't know where the dependencies come from, and if you need to test that class as a unit test, now you have to mock and build up in your tests all these 20 plus dependencies. It's a big mess in that respect. So that was solid. And basically, most of these principles, if you just follow them blindly, they will add complexity. Each module that you have might be simpler, but the overall organization will definitely be more complex. And again, these principles push people towards decoupling, more and more decoupling. I think you'll be happy to know that we're done with solid. And a bit about premature abstractions. So one of the big principles I hear spoken about is dry. Don't repeat yourself. It's about, if you have a piece of code and you have something that's almost identical, don't repeat yourself. Don't just copy it and modify it. That's the principle. I actually would say, before you actually know if you have something that is an abstraction that you need to not repeat, you actually need a few examples. You need to, you have to have 3, maybe 4 copies, and they will each be a bit different before you can say, okay, let's see what is different here, what is different there, and let's see if we can extract the commonality out to build something that, does not repeat itself. I mentioned earlier an example of if we need to change how we call our database, that would be a good example of saying, if we call it this way and this way and this way, let's see what's common there and how we can merge them. and then you have just one place which is following the dry principle. But that's only after you've seen how it works in a few places. I would also say part of that abstraction is what I call just-in-case code. So you're trying to cover all the cases. You have a specific problem in front of you that you want to solve, and you want to say, okay, I've solved it for this case. I want to solve it for, just in case this thing happens, I'm gonna write code to cover that eventuality as well. This adds complexity. One example of that is generalizing and trying to make the code work for all instances, and all edge cases. So, and not just edge cases or the actual issues that we see in front of us. Do we need to make sure that the code works in case of certain negative numbers coming in? Again, if that is something that is reasonable to expect, sure. But if it's something that you say, well, no one should be, it doesn't make sense for this system to work in such a situation, maybe you should just reject that out of hand instead of saying, I'll also make sure that I can work with this case. But again, that's just as a general thing. Don't overgeneralize. Work with what you see in front of you instead of trying to make sure that every possible situation is covered. And again, and over abstractions can lead to complexity. It's difficult to understand program flow, where dependencies come from, etc., which we discussed already. Another source of complexity is with useless code, which are things like classes that do so little they shouldn't even exist. It's wrappers that don't add much value, interfaces with a single implementation, classes that only hold one field, and design patterns that don't really add any value. So I have one code example, which happens to be in C#. And this class, filler class, it takes an integer, and that's just an instance field in it. And the only thing it has is a constructor to get that length. And the only other thing it has is a toString. And what it does here, it instantiates a new string builder. And what this line here does is basically says, create a string with the space character this many times, the length, and then it outputs it back. And this is how it is used. Now, this is poor practices in many ways, but what this is, you use string builders in order to make your code more efficient. But what we're doing here, we're instantiating not one object, but one object, and inside it when you which again, you don't really see here, but this also kind of is magical code, is that how does this produce a string is because the person who wrote this knows that when you call append, inside append, if it's not already a string, it will call toString on the object. And in the toString, we instantiate a new string builder. So there are a lot of ways of making this a lot more efficient than it is, and a lot less magical. Some of them might be just creating some very well-named constant strings, So a string called 1 space, one called 14 spaces, one called 36 spaces, and reusing them, for example. Probably here, because this is a specific format, you just need to ensure that there is the right width to the output field. And there are ways to do that better than this. But if I go back to the previous slide, what I'm trying to say is this class doesn't have any reason to exist. And this code can be simplified a lot more and be, constructed better. And over-reliance on libraries. I don't know if anyone here remembers leftpad, but I will quickly talk about that. This was an NPM library that did exactly that. It was a one-line library, essentially, that just added padding to a string on the left side of it. And at a certain stage, the author of that library, who wrote many other libraries, decided to drop it from the NPM repository. And that broke a whole lot of build systems and software systems that relied through either directly on leftpad or through other libraries that relied on other libraries that relied on other libraries that ended up relying on leftpad. Another issue is that sometimes you're going to be using a library, but you'll only be using 1% of what it does. That adds, you have all this extra code that you're bringing in, though you only need what you want. You're only using it for a very small amount of what you actually need. And I've seen examples of taking a library out and replacing it with 10 lines of code. So I would, again, then you are also in control of your code and you know exactly what is happening there. With libraries, you also can end up with transitive dependency hell. So I have a library and it relies on, let's say, a JSON library, but I'm importing another library and it also relies on the same JSON library, only on a different version. Which version wins? Are the versions compatible? Sometimes they are, sometimes they're not. And then what do? How do you solve that? Which library can you use? Which library of the two libraries can you use? Can you not use them? It's difficult to know. And to end, start with simple. Remember Gall's law, complex systems start from simple systems. So you really want to start a simple system and evolve it. Don't add new abstractions until you absolutely need them. And this also includes design patterns. You don't build them, you discover them. And I seem to have decided to tell you even again on Gall's law. And with that, do people have any questions?
Oded, thank you very much for being with us this hour. This has been an insightful session, and we hope we'll have you again, or someone from Intelligent Hack as well. It's always a pleasure to get people who've gotten the experience and expertise over the years to come and share here with us. So we hope you also had fun in the process.
I did, and thank you for having me. I hope it was useful for people, even if I wasn't able to answer everyone's question to their full satisfaction.
Thank you very much. Be safe and see you next time. Bye.
Bye, everyone.